That was in 1936. By 1949, the first catalytic reformer goes on stream. And catalytic reforming, as I'll explain the chemistry shortly, is again a fixed bed reactor that changes the chemistry of gasoline from low octane to very high octane. And actually it's the door towards producing chemicals like benzene that can go into making styrene and polystyrenes and all the derivatives of aromatics. And then lately, over the last 15 years or so, there's been really a dramatic change in specifications of the fuels that we use day to day. For example, you'll hear a lot about CARB gasoline, which is California Air Resources Board, and they've got several versions of defining the composition of gasoline. And carbob is the oxygenated blends of the gasoline. And then you hear a lot about ultra-low sulfur diesel, which is diesel that's been hydrotreated to take a fairly large amount of sulfur out of the diesel in order to meet the latest specifications. The purpose of refining is to produce a high-value product out of crude oil. Crude oil, last week actually, I asked the question, do you know how much crude oil is consumed in the United States on a daily basis? Just guess a number. I mean, does anybody have any idea how much oil we consume daily? Just the States alone. We consume 18 million barrels, not gallons, barrels. There's 42 gallons in a barrel. A barrel is a big barrel. We consume 18 million barrels a day. Worldwide, there's 75 million barrels of oil produced, roughly. It goes up and down a little bit. Okay, so that tells you how much. And of course, percentage-wise, if you look at the population, we represent maybe what, 5%, 5 or 10% of the world population, but we consume about maybe a third, 25% of the oil produced worldwide. So the idea is to take crude oil and produce all these products: fuel gas, LPG, gasoline, jet fuel, heating oil, diesel fuels that go into diesel engines, and heavy fuel oil that goes into driving big boilers that drive the ships, and coke and sulfur. And then there's also derivatives from these into petrochemicals, but I'm not going to go there. This is an example of taking roughly a light Arabian crude, which is one of the prominent crude suppliers, and then how that is translated into finished products. So from 0 to 100%, that's the volume. And you'll see like a light Arabian crude, it's got maybe about 2-3% LPG. Naphtha, which is raw naphtha, it'll have roughly about maybe 20 volume percent. Kerosene is about maybe 15-16 volume percent. Gas oils, which is the diesel, ends up being a diesel product. There's about maybe 14-15%, and then the bulk of the oil is resid. Excuse me. Now oil sells for what, about $58, $59, $60. That resid, if you try selling resid, it's about $20, $30. So you paid $60 for a $20 product, right? So economically, that doesn't make any sense until we upgrade that heavy oil. Excuse me. So after you take that oil and run it through a refinery and start looking at the different products, you find that most U.S. refineries will produce about 40 to 50% gasoline. So really, most refiners in the U.S. target the gasoline market. And then there's about 10% jet. Diesel and heating oil, we have another maybe 18%. Residual fuel oils represent about maybe 10%. And then other products like lube oils and specialty chemicals, there's another maybe 22%. I just listed here a few references that you may want to go back. We've actually, the first one is the book that most of you have received. The second book that talks about the individual technologies and economics. And there's the chemistry technology of petroleum. That's more detailed descriptions of all the different refinery technologies. And then there's a handbook of petroleum refining. And there's really an old classic, we call it Nelson. Petroleum refining somehow didn't make that list. But these are more than newer books. I'll start off with hydrocarbon chemistry first, because it's important that you understand the chemistry that goes into these different processes so that we can understand the function of each of these different units that go into this whole big complex called a refinery. This again talks about the demand between what the U.S. demand is for products versus a typical crude. This is an example of a West Texas oil. And then how we go from LPG from maybe 2-3 volume percents to maybe 7%. And then you can see the naphtha going from about 20-30% to about 40 to 60%. Kerosenes, gas oils, and then residual fuels. Again, upgrading residual fuels to finished products that have value. The atomic theory really is that, at the end of the day, we've got atomic structures which are very small components. Each element is composed of a particular kind of an atom, like you've got. And we're dealing with hydrocarbons, and you're going to see in a minute that most of these oils are really made of hydrogen and carbon, and you'll see to what extent. So if you take an oil in particular, you're going to find out that, that's okay, yeah. An oil, 84% of the composition of oil by weight is carbon. And the hydrogen only represents about 12%. So really 96% of the total composition of an oil is hydrogen and carbon. And that's why the word hydrocarbon, because it's really a true expression of what it means. And then you'll see a little bit of sulfur, nitrogen, and trace metals that actually influence the price of a hydrocarbon or an oil, is the sulfur content. That's an example of a hydrogen atom. Those that still remember some 101 chemistry, you've got an atom, you've got an electron running around outside, and a nucleus in the middle there. That's the weight of it. Let's go back still one more. No, you're going too far. Yeah, and then the carbon atom, it has 1, 2, 3, 4, 5, 6. It's got 4 atoms. What makes the carbon atom interesting is because it has 4 atoms on the outside. If you still remember your chemistry, in order to stabilize the energy level of an atom, it needs at least 8 molecules running around. And there's different ways to bond these chemicals. It could be what we call ionic bonding, or valencies that tie up the hydrogen to the carbon. And so just simply put, you need 4 hydrogen atoms in order to satisfy a carbon atom. And that's how there's a big affinity for carbon to tie up with hydrogen. And that's why the next one, which is really methane, is the lightest hydrocarbon. Okay? And methane, this is the atomic structure of really what represents natural gas that comes into your homes. There's methane. There's about maybe 80 to 90% of that gas is methane. So it's 1 carbon atom with 4 hydrogen atoms around it. And the nice thing about carbon is that you can actually then, it can bond with another carbon atom, 1 link, but then it satisfies the other 3 by more hydrogen, and that's how you start with these long links. So now as the carbon atom grows, you've got more carbon atoms together, you're going to also see the properties changing. And so we develop what is known as a boiling point curve, which is a function of your carbon content. So you'll have, maybe 5, 10, 20, 30, and as it gets heavier, you'll see that the properties of that chemical gets heavier and heavier, and you actually produce what is known as a boiling curve. And with oils, the easiest way to measure it is by volume. So what we do is we vaporize it, and as we vaporize it, we plot the temperature with the vapor, and then we create what is known as a boiling point curve, which is similar to this, but instead of with carbon atoms, these are pure components. And then, as I'll explain later, we really have mixtures of components because they have different chemical structures. So these are examples of some of the hydrocarbons and how are they bonded together. For example, propane is a C3H8. So you see all the carbon atoms kind of lined up together in a chain, and we call those straight chains, as compared to a more complex isobutane, where you see the chains now start linking, sidewise. So you'll have the carbon atom in the middle, and it's linked to 3 different carbon atoms, and each carbon atom is saturated with hydrogen on the ends of each one. Okay, so that's also a hydrocarbon, but it's an isoparaffin because it's an isomer. It's got the same overall chemistry, but yet it is not structured the same way as a straight chain is. What that does, though, is it gives us different properties, as you will see. So what you see here is the differences between this is all that's pentahexane. So these are all hexane compositions, but different structures of a C6 or a C7, so it's heptane, C7 structures. And if you look at the properties, API gravity, by the way, I'll explain that, is a measure of basically the density of a hydrocarbon. But the guys in the oil business, they decided to pick this unit of measurement, which is kind of an interesting unit. And what I did last week is I asked, that's really your quiz or problem for the week, is to go look up what is API gravity and what does it represent. And it's got a funny equation, and if you can find the origin of that equation, it would be, I think it's kind of interesting, because it tells you it's got a little history to it. Probably tomorrow I'll describe the story behind how it came about. What they tried to do, because when you look at gravities for oils, they're all they start at around a point, 0.5 for propane, and then it goes up to about a 0.8, 0.9. So you have a lot of little numbers or fractions of a number that are sometimes hard to remember. And so in order to make it an easy number to remember, what they did is they said, okay, we're going to use water as a base. We'll have an API gravity of 10. And then and it's kind of reverse, because it's 141.5 divided by the specific gravity minus 131.5. So if the specific gravity of water is 1, then your API gravity is 141.5 minus 131.5 equals a 10. And then as the gravity gets smaller or lighter, you're going to see the API going up. Okay? And I want you maybe to spend a week researching the subject. Today you go on the internet, actually it's a great resource. Just go to Google and type in the name and you'll find tons of information about the subject. So naming isoparaffins, you basically look at the longest, well, I guess most of you are not really, let's pass that one. These are examples. Paraffins, as we say, are straight chains. So all the carbons, each really carbon here is saturated with 2 or 3 hydrogens. So the ones in the middle, because you already have 2, so you're missing 2 more, so the other 2 are satisfied with 2 hydrogen atoms. The ones on both ends there, those are satisfied with a 3 hydrogen, but us chemists don't like to show that. We just show the carbon configuration right now. Olefins, which is what we call an unsaturated hydrocarbon, where you'll see 2 carbon atoms joined with 2 bonds. Okay? And then we have naphthenes, which is cyclic, but it's saturated. That's a saturated ring, known as a cycloparaffin or cyclohexane. And then you have aromatics, which have unsaturated rings in the middle. So those are double bonds, double bonds, double bonds. So that's a C6H6, because if you really add the hydrogen to satisfy that rule of 4 bonds, you'll find out you only can put 6 hydrogens there. Up on top, you need about 12 hydrogens, and then hydrogens change depending on the composition. One of the other things with olefins and aromatics, because it has that what we call unsaturated property in it, it makes it more active to react with other chemicals, whether to burn or to react with chemicals. And so you'll see a lot of petrochemicals come off the olefins and aromatics. Those are really sources, because you can tie them with other molecules and grow the molecules to make polymers and make, petrochemicals. And so one of the issues that you're going to find out is that octane, which is really a measure of the performance of an engine, to be honest. There's 2 components, octane itself, which is called an octane number, and pure octane actually has a 0 scale, and then isooctane, which is the isomer of the octane, has a much higher octane rating, which is really graded at 100. And what they do is they blend these 2 components, and then they measure the performance of an engine with the fuel that you're putting in versus a blend all the way from 0 to 100% isooctane. And if the knocking, which is a measure of how well the engine is performing, versus the other one, and then they rate the engine towards the rating on the oxygen, on the isooctane scale. What that means is that an 87 number, which is pretty much the standard fuel today, or a normal octane rating, that is it's high. I mean, it's a high octane rating, okay? But you can actually blend more high octane rated fuel gasolines to bring it up to the 89 and the 91, 92 that you see sometimes in most gasoline stations they sell today. So they sell these 3 grades that you see. You will see that as the hydrogen content comes down, the octane goes up, and then as the carbon accessibility comes down, the octane, it's okay. Let me start from the right hand side. If you have unsaturated hydrocarbons, more unsaturated, the octane is higher. Isoparaffins, the octane is higher. This is really normal paraffins. As the chain length gets bigger, of course the octane number comes down. Carbon accessibility, which is how complex are the molecules, of course if it's lower, then the octane is lower. And then the hydrogen content, the lower the hydrogen content, the lower the octane rate. A fuel needs to burn, okay, but to burn it needs to overcome a level of energy. So A plus B, like if you take a fuel plus air, oxygen, you need to activate it, and that's why we have to give it a spark, or with diesel engines you have to compress it to raise the temperature high enough that it gets to the point where then it'll start the combustion, and then once it starts burning, then it'll actually release the energy and then produce 2 other components, which is C plus D plus what we call the heat of reaction, delta E. Okay, this is an example of burning isooctane, and you can see you need 2 molecules of isooctane plus a molecule, plus 25 molecules of oxygen, so that's how much air you need to take in order to produce carbon dioxide and water. And of course the moral of this picture here is that here you take a complicated chemical, and at the end of the day you produce carbon dioxide and water. So that's what we unfortunately produce on the tail end of our engines. So in the morning when you see all the smoke coming out the back, the tail end of it, what it really is it's water. Cracking is another chemical where you take a big long chain. You remember I was saying you want to take these heavier components and break them down into lighter components. And so with cracking, what we do is we take a C20, which is a very long chain hydrocarbon, and by applying heat and some catalyst, we can actually break it down into 2, 4, 6, 8, depending on how we want to control the reaction by time and temperature, into lighter components like, normal decane or 1-decene, which is an olefin. Because one will be saturated, one will be unsaturated, because if you do the balance, you're going to find out that you just can't get two saturated components. You can only get them together if you add them together. So that's cracking. Another function we do work with is dehydrogenation. As the name implies, we're taking hydrogen out of a loop. So you take a cyclohexane, which is all saturated, and you produce a benzene. And look at the octane, what happens to the octane. RON is research octane number, which is really, when they do these engine tests to measure the octane, they do it at a low speed and a high speed, because generally engines turn on, it's low speed and then a high speed. And so they have two tests, one known as the research octane, or RON, and a motor octane, which is really the higher speed. And sometimes, if you're carefully looking when you're buying gas, they'll have an R plus M over 2, which is the average. So that rating, that 87 that you're buying, is the average of the research and the motor octane rating for that particular fuel. That's what's reported as an 87. So you can take a lower grade gasoline, 83 octane, convert that into a 100 plus octane by dehydrogenation. And these are some of the reactions that take place in that unit called reformer. I'm reforming the composition of a chemical. We actually, before we go through the cyclo, to make it cyclic, okay, we take a straight chain, and over what we call a noble metal like platinum in particular is very active catalyst, we can actually make it cyclic. So it becomes a cyclic component, and look at the octane ratings are extremely high. And it becomes what we call a blending component. You're not going to sell high octane because you're not going to buy high octane. You take a normal heptane, and I guess when I said the octane rating, what we normally do actually, it's a blend of heptane and isooctane. So the heptane, you can see the rating on the oxygen rating, that if you put heptane in your engine, man, that thing is going to be knocking all over the place. You're not going to get much power out of it. It'll be just clicking all the time. Okay? It's got a very low rating. That's really the basis for the rating. I explained the octane rating. It should be normal heptane through isooctane. Isooctane being 100 and normal heptane being a 0 rating. And we can produce a toluene, which is kind of an aromatic. And the word aromatic came because of the fact that it's got a nice smell to it. So you can make a toluene with 120 octane in it. And that's one of the reasons why every refinery will have a reformer, for two reasons. One is actually to make these cyclic components that have very high octane rating, but then the other one, look on the side there, what is it? 8 hydrogen atoms. So for every atom of normal, or every molecule of normal heptane, we can produce 8 molecules or 8 atoms of hydrogen. And hydrogen is a main component for hydrotreating all these products to improve the quality of these products. Alkylation, again, one of the units that we get involved with is alkylation. What we do there is we take 2 active components, or one, isobutane is really not a very active component, but it has a branch. So it gives it a little bit more, more ability to react easily. And butene, which is an unsaturated hydrocarbon. These are 2 C4s, C4 and C4. These components really don't have much of a value, because like down there it says it's a gas. So in normal environment, really it's a gas. And you hear a lot about LPG. Those of you that go camping, you go buy these propane bottles, those green Coleman bottles. That's really a mixture of propane and butane. Depending on the summer and the winter, we change the blend from a 30-70 to maybe a 40-60. And each state has a different spec. So we'll blend those two together and sell it as a component. So it has a very low value, though. It's not gasoline, so I can't use it as a gasoline. And a lot of these products do come out as a byproduct when I'm upgrading some of the heavier components. So we can recover it and react them together in the presence of a catalyst and mix them and produce a basically an isooctane C8 component. And look at the octane rating is 100. So it becomes it's a good blending component, very high octane rating. And do you see any sulfur in these rings? No sulfur at all. So it's a very clean fuel. Okay. And then hydrogenation. Now, look at where the sulfur sits. Sulfur it's notorious for actually sitting inside rings like that. So it makes it difficult to get to. Okay, so in order to get to that sulfur component, you really have to crack that ring. That little circle there is actually, well, it's another way of representing our chemistry. That is a ring made out of 4 carbons in the atoms there on the corners, and there's a sulfur component embedded inside. So you have to break the ring open with high temperature and a catalyst, and then react it with hydrogen in order to extract that sulfur out of there and produce hydrogen sulfide. And then we give it to Michel, and Michel can design a sulfur plant around that. Okay? Summary of product types produced from petroleum. The lighter components, which is methane, natural gas, all the way through butane, that really represents what is known as natural gas liquefied or petroleum gas. LPG, NGL, these are all different nomenclatures for that product. Okay? And then the gasolines will start around, we'll put a little bit of butane. There's a reason we put butane in, all the way to the C12s. That's your gasoline blend. So all these components that we just talked about, you blend them together to make the gasolines, and they boil either degrees C, or if you're used to degrees Fahrenheit, somewhere between 30 to about 400 degrees end point. So that's pretty much where what we call cut that component out of a crude in order to make gasoline. And then we upgrade it using all that chemistry stored in different units and blend it all together to produce 3 different grades of gasoline. And then the kerosene and jet fuel. Kerosenes you still use for lanterns if you go camping, for lighting fluids and things like that. And jet fuel is what we use in planes, predominantly jet engines. The C15 through 25, these are gas oils, heating oil, diesel oil, and lube oils. And these are used for diesel engines. And then the heavier, really heavy components, anything that boils above 750, we can really extract some heavy gas oils up to about 1,000 degrees. And heavier will actually be used for asphalts and waxy materials. Crude oil characterization. I'll give you a break, a 10-minute break. I know everybody wants to go grab, I think this, you can grab